This is Unit 4, Video 7. In this video, we will talk about molecular and net ionic equations. Now these are going to be special equations that describe precipitation reactions. So this is a precipitation reaction, which is a double replacement reaction that we've talked about, and this forms a solid. In this case, the solid is a yellow solid, and we're going to describe in detail these reactions with a special type of equation. It's going to be called a net ionic equation, very important. So we'll go step by step, and first we'll introduce and define these equations. So we've seen a molecular equation. This is the standard equation that we've written. A molecular equation simply shows the substances as compounds. And we use state symbols like aqueous if it's dissolved, and solid if it's a precipitate. And this is a double replacement reaction, so we see potassium and silver exchange places, and we get silver chloride, potassium nitrate. The standard equation, we call this the molecular equation. The next one will be called a complete ionic equation. What we do here is anything that's soluble, so for example, silver nitrate is soluble, so AgNO3, based on these solubility rules, is soluble. So we break it apart into ions, because in truth, this silver nitrate does not exist together as a compound in solution in your beaker. In your beaker, it actually exists as ions. They get split up as soon as you put silver nitrate in the beaker. They actually split up into silver ions and then nitrate ions, and these swim around, you can say, separately. So here we show them. Here's silver. Now you have to make sure you show the charge, because when you split them up, the charge becomes evident. We still put aqueous just to show that it's dissolved, and now we have nitrate with a charge of -1. Don't forget the charge. Looks like I forgot it in that one. It does exist here, so we're good. And then same thing with your second compound, which is potassium chloride. So KCl, again, is also soluble. So when you throw it in water, it splits up into ions. And you show it as K plus with Cl minus. So notice we've essentially split up your two initial reactants into ions. Now, anything that's not soluble, like silver chloride here, remains a solid. You don't split this up, because silver chloride actually precipitates to the bottom of the beaker, which means it stays together. It does not separate out. However, potassium nitrate still stays separated out. Potassium nitrate, the second product, is soluble because all nitrates and actually all potassiums, group 1 metal ions, are soluble, so you keep those separate. So notice what we've done, we've split up 3 of them. The ones that had aqueous behind them, 3 of the compounds, and the one that had solid behind it, we did not split up. Really, this is what it boils down to, the complete ionic equation. And then from here, we're going to go to the net ionic equation. Now, the net ionic equation shows only those ions participating in the reaction, and the rest are left out. So really, the only ions that reacted in this case were silver and chloride. The other ones, potassium and nitrate, actually did not react. Before and after, they stayed the same. And so we only show the ones that reacted, and technically it's the one that formed a solid, that's the one that you keep, and the one that you began with as aqueous that formed that solid. And we'll show this in detail to make a little more sense. Now, the ions that did not participate are actually called spectator ions. So in fact, potassium and nitrate are spectator ions. These are your spectators, spectator ions. They essentially exist in solution, but they just kind of swim around. They don't really do much. They spectators. They just watch the reaction, if you will. All right, so we're going to actually try this. I'm going to break it down into its parts, and we'll write all 3 equations. We're going to write the molecular equation, and then the net ionic, eventually the net ionic. In the middle of them, we'll do the full ionic. So kind of follow along. It'll be a big equation here. So we're going to write the equation for the reaction of silver nitrate and potassium phosphate. Silver nitrate and potassium phosphate. The full molecular equation shows silver nitrate. Remember, silver nitrate, AgNO3. Potassium phosphate. Phosphate has a -3 charge. It's PO4 -3. And potassium has a +1 charge, so you need 3 potassium, so K3PO4. And then we'll show these two reacting. Now, this is a double replacement reaction, so now potassium teams up with nitrate. It's a +1, -1. You get potassium nitrate. And silver teams up with phosphate. Silver is a +1 charge, so you need 3 silvers with every phosphate. Again, if you don't remember how to write these compounds, make sure you study them, come in to get help, but realize that potassium phosphate has 3 potassiums. Now, before we continue on, let's go ahead and determine which is the precipitate. We know that the first 2 are aqueous, because all nitrates are soluble, all potassiums are soluble, group 1 metals. Potassium nitrate then is also aqueous, because it is still potassium and nitrate, always soluble. Your silver phosphate is your solid, your precipitate. So this is the first equation. This is the molecular equation. We can call this the molecular equation. Really what we've done before. So this should not be new. All right, the full ionic equation is the first new one. So we're going to split up everything that exists in aqueous, an aqueous state. So silver nitrate here gets split up. The way we split this up is we put silver with a +1 charge plus nitrate with a -1 charge. You can do +1, -1, or just plus and minus. We also do the same thing for potassium and phosphate because they are aqueous. Remember, if it's aqueous, that means it exists in solution. Well, when an ionic compound exists in solution, it automatically breaks apart, splits up. That's the nature of the ionic compound. So now we're going to show potassium with a +1 charge, and we're going to show phosphate with a -3 charge. So notice the charges are seen. Now we do have 3 potassiums, so you could, if you would like, if you want to put 3, you could use this 3. However, you cannot put it down here. This would be incorrect, because this would say that the 3 potassiums are bonded together. They are not. So this actually you don't want to do. If you want to put a 3 in front, you can. I'm going to go ahead and leave it off, because in this middle step, we just care about what's there, not necessarily how many. We don't have to necessarily balance the equation, but you could if you'd like. All right, and then for my products, it looks like potassium and nitrate are still aqueous, which means we still split them up. So we got potassium plus nitrate. Now, silver phosphate is the solid one, the one we don't split up. So we'll put plus Ag3PO4. This is the only one that's not split up. And if you want, you can put state symbols next to them, but it's not necessary. Really, what this shows you is anything that's split up into ions is automatically aqueous. This is another way of showing something being aqueous. So now, so this is the full or complete ionic equation. So this is full ionic equation. And to get to the final one, which is the one we wanted to get to, the net ionic equation, what we will do is cross out anything that appears the same way on both sides. And these are the spectator ions. So what you'll notice is that nitrate has an NO3 -1 on the left. It's also NO3 -1 on the right, which means it did not change. It did not react. Nothing happened to it. So we can actually cross it out on both sides. The same thing happened to potassium. Notice potassium was a +1 on the left side. It's also a +1 on the right side. Nothing happened to it. We can cancel it out. What we are left with is actually silver plus potassium, phosphate -3, and your precipitate. So notice the precipitate, the one that has a solid next to it, is the one that's going to be left behind. And that's the whole idea. And for the net ionic equation, it's the one we want to get to, net ionic equation. You simply bring down silver with a +1. You bring down phosphate with a -3, and you bring down silver phosphate, Ag3PO4. Really, what we didn't cancel out, we just bring down and write out. Now, in this case, we do want to insert state symbols. I'll put state symbol here, aqueous here, and I'll put a solid down here. And this really shows me what reacted in the precipitate reaction. We also have to make sure the equation is balanced, so you do need a 3 in front of the silver in this case. Put a 3 right in front of here, because we have 3 silvers on the right side. And this actually is the net ionic equation that we're getting to. So we're going to practice doing a bunch of these, but this concludes video 7 of the